Hey, this is Kenneth, and today I'm going to be building a little PID controller box. So, PID controllers are essentially the thermostat for everything except for your house. Alright, somewhere in your house you'll have a little box that's got a dial on it, or maybe if you're fancy, you've got like a Nest. And all that does is it turns on and off your HVAC system to control the temperature in your house. PID controllers are essentially the same thing, but for mainly industrial processes. And so how they operate is you would have a temperature sensor. Well, so this is what they look like. So they've got on the front typically some 7-segment displays and a couple of buttons. And on the back you've got screw terminals for some sort of temperature sensor, power, and an output. This was actually the first PID controller I ever got, and I got it from China, and this was like back when I realized, like, holy crap, these things are no longer several $100s, so I bought one for myself. The PID controllers all essentially follow the same algorithm, where they have this simple 3-order model of your system, which they then use to decide when to turn on and off the output based on the input and the internal model. The problem I've had with this one is that it is a relay. The output, so the input for it is K-type only. So all I did was I wired up a little K-type thermocouple socket here, zip tied it to the controller, which then just kind of, when I'm using it, sits loose on a table. Not so great. The other problem with it is that the output on it, let's see, which should be, which is these 3 screws here, the output is just a dry relay, which would be great, except that it's on the dry relay outputs like this on PID controllers. Typically it's, at best maybe a few amps. And so it's not like you're going to be able to run. In my case, I typically drive a 1200 watt hot plate with this. You're not going to be able to run that straight from this. And so you have to wire this up to a bigger relay to actually drive your load. In my case, I built this little box, which has 2 screw terminals on the side here and an IEC plug on this side and outlets. And so inside of this right there is a solid state relay. Solid state relay is just like a normal relay, except that it's solid state. Kidding. So what this has inside of it is it has 2 input terminals here, which take 3 to 32 volts DC, and they light up an LED. There's a light emitting diode in there that turns on a set of optically coupled MOSFETs, which is fantastic because you can then switch a couple hundred volts AC at pretty skookum high currents, like 25 or 40 or however many amps that you spec them out for, right? So this is like a 40 amp. And they kind of come in this standard hockey puck package. And so one of these is mounted in there, like that, and is wired between IEC and here, right? Great, fantastic. Except that this needs 3 to 30 volts, and all this has on the output is a relay contact. So when I use this, I then also have another wall wart, which has the ends cut off, that's just screwed into this and here, and the solid state relays actually get pretty hot. So instead of this being on a heat sink like it's supposed to, it's screwed into the side of a plastic box, which probably only hasn't caught on fire yet because, gang box out of your house probably have a tendency not to catch on fire. But it certainly has gotten pretty hot, right? So what I use these for is when I'm doing any sort of sous vide, I don't have my own sous vide cooker. I just set this up with a hot plate and a pot of water. I've used it for some sterilization, stuff like that. And so I really want to put all this nicely packaged so that I don't have 120 volts on these bare screw terminals, and I don't have to plug literally end of this, which I had to borrow, so I cut it off. But this would have to be plugged into an outlet. This had to be plugged into an outlet. This had to be plugged into an outlet. Then I plugged my heater into this. It was a total mess. It just, like my kitchen isn't already a disaster the rest of the time, this makes it all that much more of a disaster. So I was digging through the e-waste pile at work, and I found these little Watlow heaters, which you'll notice, smaller, adorable, and also, instead of it being a relay contact output on the back, is what's called pulse DC, which is designed to directly drive this. So all of a sudden we've gotten rid of the wall wart. Fantastic. So now all we have to do is wire from here to the input terminals here, and the relay turns on and off. And then all we're left with at that point is that we want this all in one nice box. Before I go into that, you'll notice that this one is kind of suspiciously half as big as that one. Industrial timers and temperature controllers and all these sorts of things are all sized on as fractions of a din. I don't know what a din is or what the background is on that, but they're all fractions of it. And it seems to be pretty comically large. This one that I bought off of eBay several years ago is a 1/16 din, and then this is a 1/32 din, right? So you'll notice it's half as big. And so 1/32. Just to kind of give you an idea of how big a din is, this is a 1/4 din, right? Which you can see by the fact that it's about 4 times as big as this 1/16 din, right? This is I got a pair of these Omega PID controllers from one of my friends, and it's just silly, right? It's huge. So I haven't actually used these, but you get the idea, right? Also dry contact relays, so not going to use that one. So we've got our little Watlow 1/32 PID controller, fantastic. And the PID algorithm thing, it's a whole nother video. Solid state relay, right? I've got them in, I've got a couple 25 amps, I've got some 40 amp ones. All I need now is a box. So I was digging around, I found a box, right? So this is a 4" by 2.5" by 10" box. And I kind of look at this and going, it's exactly what I want, right? Because if I had this here, and then I could mount the solid state relay, I don't know, like that, and this would be inside it, right? So that then I'm screwed into this nice metal case instead of plastic, so there's heat sinking involved. Then I've got some space back here for the power in and power out hookups. I think we're, this is looking pretty good, right? I get some on the front. We'll have controller, thermocouple plug, and maybe a little power switch, something like that. So I think we're just gonna drill some holes and go for it. So let's go. So I've never tried one of these nibblers before. It's got a little tooth thing there, and then you can go nom, nom. I don't know. Well, we'll see. Worst case, I ruined the case, botched the whole project. You never see all this B-roll. We move on with life. Well, except for the enclosure, it'll be dead, gone, nixed, no more. Alright, well, we've got the IEC panel cut out. We've got the NEMA started. Watlow, K-type, power switch, SSR. It is now apparently 12:30 in the morning, so my neighbors probably aren't appreciating me drilling right now. So let's start in the morning. Alright, so we're back. It's the next day. It wasn't cold or rainy, so I just finished that hole up outside. Took some isopropyl alcohol and a paper towel, wiped down all the layout lines. So at this point we're pretty much ready to assemble, right? I went to fit check that one and it clicked in. So at this point it's pretty much just clicking everything in. So we got in and out on the front. We get one PID controller, one K-type, and one screw. I guess we are still missing one more hole there. Am I going to be able to drill that afterwards? Probably not. Alright, so let's back this out. So the one hole that we're missing is we've got the ground lugs on both of these. I want to take those to the case. So we're going to have to put an extra hole there for a ground stud. So given that the SSR is going to sit about like that, I think we're going to want the hole, this ground lug right there. You know, and very precisely place it, I don't know, in the middle. Yeah, that's okay. Normally, I have come in the habit, particularly at work, that I use a lot of number 6 and 8 hardware, but my hardware for 6, 8, and 10 at home is not so good. My organization system for 6, 8, and 10 hardware at home is also not so good, seeing how it's 3 unlabeled Nalgenes. So we're just going to be using all number 4 here. Come on, really? God. Wow, what a piece of garbage. So I bought a spring-loaded center punch from the Horror Fright, and it would appear that it has already stopped spring. Okay, fine. So, piece of junk from Horror Fright. We've got our center hole there. So we just need to drill that. And that's kind of been a lot of the theme for this project. Is I also got I went to Harbor Freight and kind of went nuts last week, and then I also picked up a set of 1/8 inch letter dies. Right, so these are little stamp things that you can use to stamp lettering into metal. I love it, love it, love it for keys on my keychain. The dies on this one isn't so good. It's like I tried. That may not show up. I tried stamping 15 amps max, and you can read it, but the dies are all just really bad. Is all the lettering and everything is just, there's what do you call it? Like, just there was like debris in the casting, or like little holes or pockets or something, and so there's a lot of, none of the letters come out nicely. So I mean, it's gonna work for, putting little code names on all of my keys that I use for work and for home, because who doesn't have a million different keys on their keychain? But it's not gonna make nice face plates. So I think for the front, we'll just go with label maker for the power switch. Okay, cool. So we got that. So now we're going to assemble it. The PID controller is kind of nice because all this I/O on the back actually is all screw blocks into sockets. So you can actually lift off the connector, work on it, and then when you're finally ready and you install it, and you can plug it in. So that's great for serviceability. But put all this stuff in, mount it, screw it all down, and then we can start working on the wiring harness. So here we go. Alright, so we've got everything, pretty much everything mounted, right? So we've got in and out. I put a little bit of thermal paste on here, so I think that the top of this case is probably actually going to get pretty hot depending on what the load is. So that's probably not entirely ideal, but it was either that or no heat sink at all, or try and get some fins or something on there, which I didn't really feel like doing. So it mainly depends on what your duty cycle is, right? And so maybe it'll make sense for a lot of my loads to bring it up to temperature without using this box. But then just for maintaining the actual process set point, I'll then put this in line on my heater, and so that it has a fine grain control then. But let me go. At this point, we just need to wire up everything here. So let me go dig out wires and stuff, and then we'll make this happen. So one thing I'm using here is a ferrule. It's pretty much anytime that you're putting loose wires in screw blocks, right? Trying to put that into like a Phoenix screw block, such as this one, kind of sucks. And so ferrules are literally, it's just a little tube of metal. Come on, come on. there we go, focus. Tube of metal with an insulator underneath that you just crimp onto the loose strands, and it then becomes this kind of nice, solid, ideally square terminal that you then put in your screw block. I don't have the right crimper for it yet. I ordered one and forgot to borrow one from work, so I'm just using a Gullwing contact crimper to kind of just smush it in there, which is not right, but kind of good enough. So we only need 4 of them for this project because you only need the 2 wires for power and then the 2 wires that are DC pulse to the SSR. The thermocouple, on the other hand, uses like single strand wire terminals, which are a little bit touchy. So let's keep crimping. Alright, so I think we've got all the power done. So on the load side, what we've got is we have the feed in. We've got this wire that goes to one terminal of SSR. Other terminal of SSR goes over to the load. And then return path is just a jumper from there back to the source. The PID controller on the neutral side, I managed to just double crimp it on there and run it in. I'm not a big fan of double crimping like that, and so for the L1 side, I just put 2 rings on the SSR here. Wire comes out to the power, oh man, it's upside down. Like that. The power switch with some heat shrink on it. Line then comes back over to the terminal block. Terminal block plugs in there. Ferrules on all of those. And then these 2 are the DC pulse. All right, and this is the part that's really nice about a DC pulse controller versus a relay controller, a relay output, because we don't need a 12 volt power supply in the middle here. This just wires straight up to the SSR and can drive it. Right, so that's why that's so nice. It makes this a little bit cleaner. At this point, all we've got left is the thermocouple wire. Right, and so we've got one of these blocks that then again plugs into here, and these terminals are pretty squirrely. As you see, they've got a little button and a hole. And what you do is when you push the button, it opens up the hole so you can stick the wire in it, and then when you release the button, the wire can't pull out of it again. For this design specifically, I'm planning on using K-type thermocouples, which are usually color-coded as yellow. And so typically, it's not unusual to see just copper wire run from here into the terminal block. The concern then is that this connector here becomes the cold junction for the thermocouple. Because how a thermocouple operates is that you have 2 dissimilar metals that are touching, and any 2 dissimilar metals that are touching actually produce a voltage. Thermocouples are made out of very specific pairs of metals that produce a voltage in a very predictable and somewhat linear way, right? Which is why you have K-type, J-type, E-type, N-type. All these different types of thermocouples are just different pairs of metals that tend to operate well at various temperatures. But the problem is that on the end of your thermocouple, you have this junction between these 2 metals for a K-type thermocouple. That produces a voltage. But at your connector, you then have each of those 2 metals to copper, and that produces another voltage. But thankfully, they're both going to copper, so I think it kind of cancels out as long as you know what temperature that joint is at. The issue is this junction, and that's called the cold junction reference. And so in the PID controller, it has a temperature sensor that is sensing the ambient temperature and assuming, okay, this connection is at 22 degrees Celsius. So the voltage coming out of the K thermocouple is relative to 22 degrees Celsius. The problem is this panel mount here is on our heatsink for the SSR. So I don't know how hot this connector is going to get, how much warmer than here, which means that this is going to start misreading if we just have copper wire running there. I may be wrong here. I think if I use thermocouple wire, K-type thermocouple wire from here to here, I think it then cancels out and this just becomes a continuation of the thermocouple. Not that I think it really matters, because like everything I'm doing typically is like bringing water up to 65 degrees Celsius for yogurt, but we're gonna see. So I believe K-type, yeah, so K-type has two wires inside it, one of them's yellow, one of them's red. The red one, I believe, is negative. Right, come on guys. So I'm gonna try and wire that up and we'll see how that goes. Alright, so we're out in my living room now just because that's where I've got space right now. And I've buttoned this up. Haven't put all the fit and finish on it. We're going to put little feet on it and some nice labels. But the main thing is we've got power coming into it, and then we've got this hot plate plugged into it. I then just have a piece of aluminum on the top here with a thermocouple jammed into it, plugged in here. I've run an auto tune on this piece of aluminum on here, so it's going to behave particularly well, but that's kind of operating one of these PID controllers is a separate video. The main thing is that we can now, I've got the controller powered off, so presumably I'm like plugging everything in, everything set up, and now I'm ready to go. So I turn it on, it boots, and it reads out 22.5. Holding the set button, we can see that I have the process value, or the set value at 50C, and so it has turned on. Well, there's a little LED here that shows, but yeah, don't need to stir. You can see that the heater has come on, and so now the temperature is starting to rise. Right, so 23.7, 23.8. It's fantastic. Right, and then if we hold set. Right? Yeah, if we hold set, we can lower the set value. So let's put it at like 35. Alright. So now it stores the new 35, and then it's going to target it. I can turn that up a little bit. As far as what we can use this for at this point, I mainly use this for hot water baths. So I do yogurt fermentation with this setup now. Right. Well, what it used to be was a whole disaster of wires and then this hot plate with a pot of water on it. But I mean, now this is much cleaner. Yeah, I can't feel it yet. All right, and so you'll notice, getting back to this, you'll notice it's turned off, but we haven't reached the set point yet. Right, and that's the great thing about PID controllers. They're more intelligent than the thermostat in your house, because it knows that even though it hasn't reached 35C yet, it's put enough heat into the system that this hot plate and the aluminum block is actually going to coast much of the way to 35C, and so it doesn't need to apply any more heat, right? So that's why we use PID controllers instead of just thermostats, right? Because a thermostat would be heating all the way up to 35, and then we would grossly overshoot it, and then as the system does eventually cool off and get below 35, it would heat it and it would overshoot. All right, so great. All right, so you'll notice we're coasting up, 34.4, 30.5. Things I actually use this for though, pot of water, I put jars of milk in it, pasteurize the milk, and then I set this down to a lower value, drop in some, like a spoonful of yogurt in each one with active cultures, and a couple hours later I've got, you know, several jars of yogurt, right? So I do, for breakfast I'll have granola with yogurt on it, much like cereal with milk, but, you know, granola and yogurt, which is fantastic. So you'll notice we did overshoot a little bit here, but it is really quite slowing down. And it'll then come back and settle into the 35 quite nicely. Auto tunes on these tend not to do a good job of getting it so that you don't overshoot, because kind of the fastest way to get to the process value, the set value, is to, you know, overshoot it once and then settle back into it. But if you really cared about not overshooting your target and you only wanted to come up to it as quickly as possible, then you would obviously not use the auto tune feature in your controller, and then you would instead measure the impulse response of your system and calculate your own coefficients. Right, separate thing. So yogurt, I also do a sous vide with this, right? This is essentially just a sous vide controller here. And so one of my favorite sous vides is actually soft boiled eggs, because they come out fantastic when you don't have to try and time it exactly right. But I don't know, I mean, that's didn't really feel the SSR get hot at all. And it was maybe there. So here, let's put the set value up at something high. Alright, I'll play with it. Anyways, this is what I got. It's not perfect. Of course, you know, you should do better. But I hope you enjoyed watching me put this thing together. And thanks for watching. See ya.